Hi everyone, this is Mrs. G8 and today we are going to be reviewing some right triangle trigonometry. But first, please pause the video and give this warm-up a try. All right, go ahead and check your work. So here we are finding a missing side length of a right triangle. We can see that because it has this little square here, we know this is a 90-degree angle making a right triangle. So we know that the Pythagorean theorem must be true for all right triangles, and it states that a squared plus b squared equals c squared. Now the thing to watch out for is that c must be the hypotenuse. So you can see that I drew an arrow across from my 90-degree angle because that's how you can always identify the hypotenuse. So in example A, x must be c, and example B, root 13 must be c. And then from there, you simply plug in your other values and you solve for x. I do want to point out, like in a step like this, here I'm taking the plus or minus square root of both sides. However, if x represents the side of a triangle, we know that triangle sides can't have negative lengths, so it's just always going to be the positive answer. But I don't want you to forget that technically we are taking the plus or minus square root of both sides. All right, so there are 6 trigonometric functions that we are going to learn about this year, and those are sine, cosine, tangent, cosecant, secant, and cotangent. So all of these functions can be defined by the ratio of different sides of a right triangle. So here you see we have a right triangle, and this, just so you guys know, this variable is the Greek letter theta. It's probably the most common variable that we use to show an angle. And then remember, this square means that this is a right angle. So if this is theta, if you look at the leg that's touching the angle, we call this the adjacent side. Adjacent means next to. And then if you look at the leg that's across from the angle, we call that the opposite side. And then the side that is across from the 90-degree angle is always going to be the hypotenuse. So depending on where your angle is, of course, the adjacent and the opposite side could swap. If we're working with this angle up here, then this would be adjacent and this would be opposite. But the hypotenuse should always be the same. So like I said, we can define these 6 trigonometric functions as ratios of different sides of a right triangle. So if you have the sine of theta, it will be the length of the opposite side over the length of the hypotenuse, opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. You've probably heard the phrase SOHCAHTOA, and this helps you memorize those ratios. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So cosecant, secant, and cotangent, we call these 3 functions the reciprocal functions because their ratios are the reciprocals of the first 3. So if you look at secant, or cosecant right here, it's hypotenuse over opposite, which is the reciprocal of the sine ratio. If you look at secant, it's hypotenuse over adjacent, which is the reciprocal of your cosine angle. And if you look at cotangent, it's adjacent over opposite, which is the reciprocal of your tangent angle. So again, if you know the first 3, and you know which ones are reciprocals, then you know the second set of 3. Now, since these are also reciprocal functions, we can also write cosecant as 1 over sine. We could also rewrite secant as 1 over cosine, and cotangent can be rewritten as 1 over tangent. And the last thing I want to point out, and you'll see when we write these functions in math expressions, they are abbreviated. We're not going to write full sine, we use SIN. We don't write out cosine, we write COS. So these abbreviations are just written. When we read them, I would still like you to say sine, cosine, tangent, cosecant, secant, and cotangent. So again, I don't want to hear tan theta, cos theta. I want to hear the full name of the function when you read it. So these, again, are ratios that you do need to be comfortable with. You do need to have them memorized. As we move forward, we're going to practice today evaluating these expressions given right triangles. All right, let's look at this first example together. Here we're going to evaluate the 6 trigonometric functions of this angle theta. So you'll see that we are given the adjacent side length. I'm going to label this A for adjacent. And we're also given the opposite side length, but you'll see what we are missing is the hypotenuse. So the first thing I'm going to need to do is do the Pythagorean theorem, a squared plus b squared equals c squared, to help me identify that missing side length. We need all 3 if we're going to name all 6 trig ratios. So we can say 5 squared plus 12 squared equals c squared. So 25 plus 144 equals c squared. And that gives us 169 equals c squared. So c is going to be 13. And I'm going to label this hypotenuse. Okay, so let's start with the sine of theta. So we remember that sine is opposite over hypotenuse, so that ratio would be 12 over 13. We can do cosine of theta, which is adjacent over hypotenuse, so 5 over 13. And then tangent of theta is opposite over adjacent, so 12 over 5. Now, for the 3 reciprocal functions, I'm going to put cosecant theta right next to sine because they are reciprocals of each other. So if the sine of theta is 12 over 13, then the cosecant of theta is 13 over 12. And secant is going to go right next to cosine. And I'm going to do the reciprocal of 5 over 13, which is 13 over 5. And cotangent theta will be the reciprocal of tangent of theta, so it'll be 5 over 12. So there's our 6 trigonometric ratios of theta. All right, let's try another problem together. This one says, in a right triangle, theta is an acute angle, and the sine of theta is 4 over 7. Evaluate the other 5 trigonometric functions of theta. So here, we don't have a picture of a right triangle, so we are going to need to draw our own. So let's go ahead and do that. And I'm going to always put my right angle. Now, it said that theta is an acute angle, meaning it could be either of these, right? An acute angle is an angle less than 90 degrees. So if this angle is 90 degrees, both of these are going to be acute. So I would say pick one of them and call them theta. Now, if they tell us that the sine of theta is 4 over 7, that means that the opposite side length is 4 and the hypotenuse is 7, right? Because sine is opposite over hypotenuse. So you can see that we have 2 sides of our triangle, so we need to find this missing leg. I do want to point out that since we have the hypotenuse, this must be the c value, and then this is the opposite side. All right, so let's use Pythagorean theorem here. So we have 4 squared plus b squared equals 7 squared. 16 plus b squared equals 49. B squared equals 33. So b is the square root of 33. Super, super common to have values that are radicals with our trig problem. So don't be afraid if one of your side lengths is a radical. That is totally fine. And that's going to be our adjacent side. All right, so we already know that the sine of theta is 4 over 7. I'll just write it again. We can find the cosine of theta, again, by doing adjacent over hypotenuse, so root 33 over 7. The tangent of theta will be opposite over adjacent, so 4 over root 33. So now here, With these radicals, we do have to remember our rule that we don't like to leave radicals in our denominator. So we will need to rationalize. And I can rationalize this simply by multiplying the denominator by itself by root 33. So we get 4 root 33 over 33. And I know that makes it look a little more complicated than the original, but again, this is simply a rationalized expression. Okay, now let's do our reciprocal functions. I'm going to put cosecant right next to sine, and I am just going to flip my answer here. So 4 over 7 becomes 7 over 4. For secant, I'm going to flip the ratio from cosine. So 7 over root 33, and here I do need to rationalize. So we get 7 root 33 over 33. And for cotangent, I'm going to take the reciprocal of the original ratio I wrote, which just gives me root 33 over 4. So I don't actually need to rationalize that one. So there I have found the other 5 trig ratios. Just remember, sometimes you'll be given information and you're going to be the one that needs to draw the picture. So if you don't have a right triangle and you're doing a trig problem, it's usually a good thing to draw in. All right, I have one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work. So here you are given tangent of theta. So you set up your triangle, but this time the opposite leg is 3 and the adjacent leg is 8. So you need to use Pythagorean theorem to find your hypotenuse. And then once you have that set up, you're simply following your trig ratios, and make sure you rationalize your denominator for sine and cosine. All right, so now we're going to take a quick break from our trigonometric functions, and we're going to talk about our special right triangles. So there are 2 special right triangles. They're called 30, 60, 90 triangles and 45, 45, 90 triangles. And you can probably guess that they are named after the angles within the triangle. So both of these triangles are extremely, extremely important. You need to be able to memorize and replicate these triangles. So for any 30, 60, 90 triangle, the relationship between the 3 sides is always going to be the same. So first, when I draw the picture, I always remember the numbers 1, 2, root 3. I say 1, 2, root 3. 1 is the smallest number, so it has to be across from the smallest angle. 2 is the biggest number. 2 is a little bigger than root 3. So it has to be across from the biggest angle. So that means that root 3 should be the remaining side. So if you can remember 1, 2, root 3, you should be able to place these. So if you know these side lengths, there's always the same relationship between the sides. So if you are going from short leg to long leg, short to long leg, to go from 1 to root 3, you simply multiply by root 3. So this will work for any 30, 60, 90 triangle. Even if it doesn't start as 1, if you have the short leg, you multiply it by root 3, and that will give you the long leg. And then if you look at the relationship between the short leg and the hypotenuse, sorry, this was supposed to say leg, not let, you can see going from 1 to 2, it's doubled. So if you want to go from your short leg to your hypotenuse, you multiply by 2, or you double it. And of course, to go backwards, you would do the opposite. Hypotenuse to short leg, you divide by 2. Long leg to short leg, you divide by root 3. So if you know these relationships, it will really, really help you, because these are super common angles and super common triangles that we will be working with. Now the other one is a 45, 45, 90. So since the 2 angles are the same here, of course these 2 side lengths are going to be the same. And the relationship, you have to remember the numbers, 1, 1, root 2. 1, 1, root 2. So if I'm going from leg to leg, well, it should always just stay the same. This is an isosceles triangle because the base angles are the same. And if you're going from either leg to the hypotenuse, you multiply by root 2. And of course, if you need to go backwards, do the opposite. Just divide by root 2. So these two triangles, again, you should be able to memorize them and replicate them. A lot of people, as soon as they get their trig quiz or test, they're going to draw in their two triangles and mark up the 3 side legs. So that would be something I absolutely recommend that you do. All right, let's give these two problems a try. We're going to find the missing sides of the following SRTs, which stands for special right triangles. So again, if we use the ratios we already know, these problems are actually really quick and easy. So I'm going to recreate my little 30, 60, 90 over here, my own. So 60 degrees, that makes this 30 degrees. And we know the relationship again is 1, 2, root 3. 1, 2, root 3. The short leg is always 1, the hypotenuse is always 2. So here you can see that I have the short leg. I have the short leg. So if I want to go from short leg to hypotenuse, right, I'm going to double it. So that means that A equals 6, right? Short leg to hypotenuse, I multiply by 2. And I know that short leg to long leg, I multiply by root 3. So I take 3 and I multiply it by root 3. So B equals 3 root 3. All right, let's look at part B. So I'm going to draw my own little 45, 45, 90. I usually like to try to match the same orientation. And remember, it's always 1, 1, root 2. So here I see that these legs should be the same. So that means V is 7. And remember, to go from leg to hypotenuse, I multiply by root 2. So U is 7 root 2. So if you know your special right triangles and you know the relationships between the sides, these problems are super quick and easy. All right, let's do a couple more together. So here I have another 30, 60, 90. We know this would be 30 degrees, but this time I'm given the long leg. So if going from short leg to long leg, I multiply by root 3, that means if I'm going backwards from long to short, I should divide by root 3. So for y, it's going to be 3 root 3, and then I divide by root 3, which just gives me y equals 3. And then once I know that this value is 3, I know that going from short leg to hypotenuse, we multiply by root 2, or by 2. We just double the value, so that means that x is 6. So there you go. Let's look at part B. So here we have another 45, 45, 90. Again, I have to work backwards because now I'm given the hypotenuse. So short leg or leg to hypotenuse, I usually multiply by root 2. So if I'm going backwards, I'm going to divide by root 2. So that means that n is going to be 6 root 2 divided by root 2, which is just 6. And I know that m will also equal 6 because the two legs should be the same. All right, and for this last one, here I am given the hypotenuse. So the first thing I'm going to do is work my way backwards to the short leg. Again, short leg to hypotenuse, I multiply by 2. So hypotenuse to short leg, I should divide by 2. So that means that n is going to be 7 over 2. And then I follow my next pattern. I know that from short leg to long leg, I multiply by root 3, so times root 3. So that means n is going to be 7 root 3 over 2. And there you go. So sometimes we're going to be working our way backwards to get to our short leg or to go from hypotenuse to leg on a 45, 45, 90. And then sometimes we'll be working our way forward. All right, go ahead and pause the video and give these 3 a try on your own. All right, go ahead and check here. So again, leg to hypotenuse, we multiply by root 2. So A is going to be 5 root 3 times root 2, which is 5 root 6. And of course, our two legs should be the same. So B is also 5 root 3. For part B, I need to work my way backwards from hypotenuse to short leg, which would be dividing by 2. So that means that B is 10. And then from short leg to long leg, I simply multiply by root 3. And then here, long leg to short leg, I divide by root 3, giving me 10. And then short leg to hypotenuse, I multiply by 2, which gives me 20. All right, so now we're going to see if we can use our special right triangles to help us fill out this table that has trigonometric values for what we call our special angles, which would be 30 degrees, 45 degrees, and 60 degrees. So first thing I'm going to do is just mark up the sides of my triangle. So again, we have 1, 2, root 3. 1 is the shortest leg, so it goes across from the smallest angle. 2 is the largest value, so it should go across from the largest angle. And then for my 45, 45, 90, remember this means that these two angles are congruent, which means these must be 45. It's always 1, 1, root 2. Okay, so let's use SOHCAHTOA, our trig ratios, to see if we can fill out this table. Sine of 30 degrees. Here's 30 degrees. If I do opposite over hypotenuse, it's 1/2. Let's do the cosine of 30 degrees, which would be adjacent over hypotenuse, which is root 3 over 2. And then tangent would be opposite over adjacent. So 1 over root 3, which if we rationalize becomes root 3 over 3. Then for cosecant, I know that cosecant is the reciprocal of sine. So instead of 1 over 2, it becomes 2 over 1. I know secant is the reciprocal of cosine. So 2 over root 3, which becomes 2 root 3 over 3. And I know that cotangent is the reciprocal of tangent. So 1 over root 3 just becomes root 3 over 1. Okay, now let's do our 45 degree angle. And we can use either one. If I'm using this one, sine is opposite over hypotenuse, 1 over root 2, which is root 2 over 2. Cosine is going to be the same, 1 over root 2, which is root 2 over 2. Tangent is opposite over adjacent, 1 over 1 is 1. And then for cosecant, I'm going to take the reciprocal of sine, so it becomes root 2. Same for secant. And for cotangent, the reciprocal 1 is just 1. And now we can do the same for our 60 degree angles. I'll start with sine. So opposite over hypotenuse is root 3 over 2. Adjacent over hypotenuse is 1 over 2. And opposite over adjacent for tangent is root 3. Cosecant will be the reciprocal of sine, so it becomes 2 root 3 over 3 once I, again, rationalize just like here. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent, so it becomes 1 over root 3, which is root 3 over 3. So you can see that for some of these values, they are swapped. So for sine, for 30 degrees, we have 1/2, and then for cosine, we have root 3 over 2, and it's the opposite for 60 degrees. The sine is root 3 over 2, the cosine is 1/2. So you can see that a lot of these values kind of repeat themselves, but they are swapped for sine and cosine for different angles. But again, we can always use our special right triangles to help us evaluate these expressions. So if you have a 30 degree, a 45 degree, or a 60 degree angle, you should be able to tell me the exact value of these 6 trig functions. And you can always draw the triangle if you need to. All right, so now we're going to use our trig expressions to help us find missing sides of a triangle. And this time we are going to need to use our calculator to help us because these are going to be values that are not 30, 45, or 60 degrees. So here I see that I'm given one angle of a right triangle. I want to find the adjacent side, and I'm also given the hypotenuse. So here I'm asking myself, well, which trig function uses adjacent and hypotenuse? And I know that would be cosine. So I can set up an equation that says cosine of 52 degrees equals x over 17. Now all I need to do is solve for x. So I'll multiply both sides by 17. And then this is something we will plug into our calculator to get a decimal approximation for. It is important that you make sure your calculator is in degrees. And so we get about 10.5 degrees. I'll round to the nearest tenth. Okay, let's try another one. And actually for this one, just for the sake of practice, can we cross this off and move it over here? Okay, so for this one, if I do that, you'll see what I am working with is the opposite side length and the hypotenuse. So if I ask yourself, okay, which trig function involves opposite and hypotenuse, it'd be sine. So the sine of 29 degrees equals 15 over x. And so now I need to solve for x. So I'm going to start by multiplying both sides by x to get it out of the denominator. And then I'm going to actually divide both sides by the sine of 29 degrees. And then this is something we can plug into our calculator. And we get about 30.9 degrees. Don't forget your units. You do need to have that little degrees symbol. Okay, and then this last one, what we would have here is the opposite and the adjacent. So if you ask yourself which trig function uses opposite and adjacent, it'd be tangent. So the tangent of 32 degrees is 16 over x. I'm going to multiply both sides by x. And then I can divide both sides by the tangent of 32 degrees. And then from here, just using our calculator, and we get approximately 25.6 degrees. And there you have it. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. So here I have the opposite side and the hypotenuse, so I set up an equation with sine. There's my answer, and for this one I have the opposite side and the adjacent side, so I set up an equation using tangent. All right, the last thing we're going to do are a couple word problems. So these are going to be angle of elevation word problems, which are really common for right triangle trigonometry. So this says a parasailer is attached to a boat with a rope that is 72 feet long. The angle of elevation from the boat to the parasailer is 28 degrees. Find the parasailer's height above the boat and round to the nearest tenth. So first, let's kind of draw a picture. Here's a boat, and we know that it's attached to some parasailer, so up here, with a rope. And it says that that rope is 72 feet. Now, whenever you see the phrase angle of elevation, that angle of elevation needs to be drawn from a horizontal line. So you can imagine here's the water. Let's give that a horizontal line. So the angle between the horizontal line and the rope will be that angle of elevation, and that is 28 degrees. And they want to know the parasailer's height, which would be this distance, and then this makes our right triangle. So this is what we are trying to find. So then this is just like the last examples. I look at and I say, what do I have? I have the opposite and the hypotenuse. So I can say sine of 28 degrees equals x over 72. So x equals 72 times the sine of 28 degrees. We'll plug that into our calculator. We get about 33.8. And then we'll just want to make sure we include units for our final answer. So the most important thing here is to remember we always draw an angle of elevation from a horizontal line. It has to be touching a horizontal line. All right, here's the last you try. So again, pause the video and give it a shot on your own. All right, go ahead and check your work here. So we could see that here's the ladder that's leaning against the wall, and that ladder is 8 feet. Here's that angle of elevation, which is 53 feet, and this time they ask how far is the base of the ladder from the wall. So this is the distance we're trying to find. So since we have the adjacent side and the hypotenuse, I'm going to use a cosine function to help us create the equation, and our final answer is about 4.8 feet. All right, that is all for today's video. Thank you so much for watching.